Hello, hello, hello. Simon Whiteley here. So welcome to my latest live stream. This is the second live stream in a series of live streams where I'll be working through the a case study involving the Boeing Starliner and the crewed mission where they had, just bear with me a second, trying to run a live stream at the same time. Let's just mute this. There we go, that's it. I'm just getting used to this. I've been doing live streams on LinkedIn for a little while. And now I'm trying to use my YouTube channel and see whether the live stream is easier to facilitate, better for you, or whether I should just stick with LinkedIn. So just bear with me. And of course, if you have any sort of questions or comments, there is a comments box on the side, a chat box you can type in there, and I should be able to bring that up on screen and answer your questions. And of course, if you're looking at watching YouTube but you don't have a YouTube account and you're not able to chat, I'm going to try and use the LinkedIn post for this event, so you're welcome to add comments to that, and I'll see if I can bring those up on screen as well. So yeah, welcome. So my name's Simon Whiteley. I'm a System Safety Engineer Consultant from the UK. I specialise in STAMP, STPA and CAST. I provide coaching, training, consulting, facilitation and independent review in support of individuals who are on their journey learning this themselves, trying to be a pioneer in their organisation, or I also help large organisations in their journey using STAMP, STPA or CAST. Now, if you haven't seen the previous live stream, essentially what I did is I went through the official investigation report, gave a bit of an overview of it, started to talk through the executive summary to sort of give a flavour of what this particular incident is all about. Now, bearing in mind, my experience with this is relatively minor. All I've done is read that first part of the investigation report. And so as we go through this today, I will essentially be reading it for the first time and talking about things through the lens of STAMP, through the lens of STPA. So if you're not too familiar with those terms, so STAMP is System Theoretic Accident Model and Processes, and that label, that acronym, essentially refers to some ideas, some principles, a new accident causality model, which instead of being focused on failures and responding to failures to prevent accidents and hazards, it focuses on what's called control, inadequate control. And the concept is very much about control structures and control loops. And if you're involved in engineering, control loops will be relatively familiar with you. And essentially it treats accidents as complex dynamic events that involve instances of inadequate control. And they could be due to failures, traditional failures, or they could be due to, what I call dangerous successes. So the system has behaved as designed, and that design is inadequate in some shape or form, and that has resulted in an accident or a loss. And so the purpose of STAMP is essentially to change that emphasis from just looking at failures and causes of failures to looking more broadly and including dangerous successors, inadequate control. Now, STPA, System Theoretic Process Analysis, is a hazard analysis method that essentially is based on STAMP, and you use that during system design and development or system change, essentially a hazard analysis method. And then, of course, CAST, causal analysis using systems theory. That is an accident or incident analysis method, which you essentially use in the aftermath of an incident or accident. And you look backwards with information and use the principles of STAMP to understand what has happened in that accident and how we can go about preventing it in the future. So STPA is much more, detail focused. It looks at all possible causes of an accident, whereas CAST focuses on the specific causes of the accident, the specific issues with the control structure model that were evident in a particular incident. So again, whilst we are talking about STAMP, STPA and CAST through the lens of this case study, I'm going to try and talk about those aspects from both directions. Pre-accident, trying to prevent an accident, anticipate the issues with the system, and then post-accident through the lens of an investigation analysis method. And as I said, if you've got any questions or comments, please stick them in the chat. And of course, if you want to talk to me personally, you've got a concern with something and you want some help, you want to have a conversation, you are welcome to get in touch with me via my website or via LinkedIn. And I'll just put this up on screen. There we go, it works. Look at that fantastic green screen. Okay, yeah, if you want to get in touch, you need some help and support. If you want to visit my website, whiteley-safety.co.uk, click this big green button here, I need help now. Put your details in there, send me a message, we'll set up a call and I'll answer your questions. And if you need some help, we can talk about what that might look like. And of course, if you want some foundation training in CAST and STPA and STAMP, I do have a one-day online course that's available for anybody around the world to join. I've just completed the first quarter of 2026 training cohorts, and I'll be releasing some dates for the next quarter. And of course, if you want some training specifically for you personally, as opposed to a public group, I can make a proposal for you. And again, if we're not already connected on LinkedIn, please visit my LinkedIn profile. Send me a message on there, connect with me, and we can maintain trust that way. Okay, so let's talk about this then. So this is a space case study. This involves the Boeing Starliner spacecraft, which you can see there. And essentially what happened is they had some issues with the propulsion system when they were on orbit. And, it could have been really, really, really serious. I mean, it was serious as it was, but it could have been so much worse. And of course, there's the recent launch of a different spacecraft yesterday, which is really exciting. Really looking forward to seeing how that plays out. Best wishes to everybody and Godspeed to the crew. But this is a completely different spacecraft. This is not the one that was launched yesterday. Okay, so there is an official investigation report which was issued by the investigation team in February 2026. So this is, quite a while after the accident occurred. And of course, they've not used the stamp-based approach, CAST, to do the investigation. So of course, there'll be some points that I make, some comments that I make. I'm not trying to, pick on these individuals or, anything like that. I'm just looking at this investigation through the lens of STAMP, STPA and CAST and providing some, raw comments on it. So I don't mean anything by the things I say against individuals or organisations. This video, this live stream is essentially to share learning, to promote learning of new ways to do things, hopefully better ways that can find more causes of accidents more quickly, and generally make everything safer and better performing and save some money at the same time. Okay, so let's have a look. So the investigation report is broken into broadly 8 sections. So we've got the scope of the investigation, section 1, additional investigations. So there were 2 other investigations that went on in parallel to this one, and I think they're potentially still ongoing, some of those. There's the crew commercial program, CCP background, the technical root cause analysis, RCA and findings, and then of course section 5 is culture and decision making process during the mission, and then 6 is root causes, 7 is additional observations from the investigation team, and the 8 is consolidated recommendations. Now there are 2 fault tree analyses that are included in this report, but the quality and resolution of them is not that good, so you can't really tell too much, apart from they are quite broad, quite high level. And of course, I wouldn't expect them to stick real detailed fault trees in the publicly available report, because that just goes a little bit too far. And then there's various appendices with various information from the other investigations that took place. So let's give a look. So we went through the executive summary last time. If you want to rewatch that, there is the link in the LinkedIn comment. But I think it's also on my YouTube channel. If you click on my YouTube channel and go to live streams, you can click straight onto that. So let's get stuck in then. Let's go for section 1, investigation scope. Actually, before I do that, I just want to say this will be a series of live streams, because this is quite a large report. It is 311 pages. I don't intend to read every single page word for word, because it's not really necessary. I will read the majority of the body of the report, but I will need to break this up into a number of live streams. And of course, once it's recorded, once it's not live, you can watch it at double speed if you want to, so you don't have to worry about that. So yeah, section 1, scope of the investigation. Here we go, everybody. So I'll get it on the screen so it's nice and big. And then before I get stuck in, I'm just going to have a drink. So this is a Christmas present from my wife. If you can see that, it's an SR-71 Blackbird on my pint glass. How cool is that? Bit of an aviation geek. Don't get me started on that. Right, here we go. So, scope of the investigation. Mission background. The Boeing Starliner crewed flight test represents a critical milestone in NASA's commercial crew program. Certification of Starliner as a US commercial spacecraft to transport astronauts to and from the International Space Station. So like in the previous video, I'm just going to highlight some of these because some of these entities, some of these organizations, these people, these nouns, they are potential candidates for inclusion in our control structure model, which is a core part of doing any kind of stamp-based analysis. So Boeing is a design organization. There'll be some, people involved in that, obviously. There'll be some teams doing various different things. There'll be some procedures and processes for the way they do things. And of course, there'll be documentation of the things that they do and their safety assessments and things like that. So the reason I'm highlighting this is I'm just trying to stretch your mind, open your mind to the broader concept of what each of those words, those labels imply. There is a lot behind those words, and the reason I'm talking about this and emphasizing it so much is one of the key skills of building control structures and being successful at using STAMP, STPA and CAST is the ability to identify candidates for inclusion in your control structure and being able to decide whether they should meaningfully be in the model, because you don't want to make your control structure model too big, but likewise you don't want to miss important but subtle details, and you have to decide that as being a modeler. You get to decide what you should include and what you shouldn't. And of course, if you're doing the design of something, you will include a different scope than if you were doing an investigation. Because of course, if you're doing an investigation, you build a control structure. There are certain parts in that control structure which were working perfectly fine and didn't contribute to an accident. And you may not have the time or resources or need to go and look at those parts of the control structure. So it'll be necessarily narrow. Not in all cases, but some cases. So Boeing as an organisation, I would include those in the control structure model. Starliner crewed flight test. So that could represent a test program. So that involves certain phases, certain organisations, handover of information between each other, important decisions such as the key decision: is this platform safe and ready to go and be operated as part of a mission to space? Yes or no? What is the criteria behind that? What is the decision making behind that decision maker? Who is that decision maker? There'll be a number of stakeholders involved in that. And of course, given that this thing went to space, with these issues, design issues, etc., why would it make sense for that stakeholder, that decision maker, to say, yes, let's go flying? So yeah, I'm just stretching your mind a little bit. So the flight test represents a critical milestone in NASA. So again, they're an organisation that need to be present in the control structure model. Commercial crew program. So again, that can represent an organisation and some people with some decision making and processes and things like that. Certification, that's a specific process that has certain milestones and activities. And then, of course, Starliner is the vehicle itself. And then the US commercial, so United States as an entity with a government and government departments and regulations and laws and all of that good stuff. Commercial spacecraft to transport astronauts. So they are real people that will be on board this thing, in control of this thing, influencing this thing. They will be subject to a training program of some description, and that training program will be informed by the designer and how they've designed the spacecraft and the safety assessments they've done. And they'll be going to and from the International Space Station. Again, that is well, there's the physical thing, but then there is the organisation that operates it and the people on board and how they interact. And of course, the decisions, the ground control, they will make decisions about whether the spacecraft should approach the space station and, how they should coordinate. So Starliner was launched on June 5th, 2024 from Cape Canaveral Space Force Station, carrying NASA astronauts Barry Butch Wilmore and Sunita Sonny Williams. I saw a great photo of those guys at the launch on LinkedIn. It's fantastic. I'm so jealous. I'd love to have been there. To the ISS, initially planned to be an 8 to 14-day mission. The flight was extended to 93 days due to technical anomalies. So these are the propulsion issues that were going on. Now, of course, it's important to be mindful that these anomalies, they are, emergent properties of a complex system. So they could be very simple technical failures, of course, but you'd like to think that an organisation developing something as complex as this will be, they'll have good processes for identifying and dealing with failures, and of course mitigations associated with those. So that technical anomalies could cause such an issue it's a hint that something more broad is going on here, not just to do with the physical spacecraft, the system, but with the organisation that designed and created, built and operated this thing. So these anomalies ultimately culminated in an uncrewed return of the Starliner capsule to the White Sands Space Harbour on the 7th of September 2024. And I said in the last video, the reason I'm using different colours is I tried to have a bit of a system for highlighting this information. So the orange ones imply that they are candidates for inclusion in my control structure model. So I need to trace the origin of those controllers. And the yellow is just emphasising time event-based information. So when you're doing an accident investigations, typically one of the things that you will do is you will create a timeline, a sequence of events to try and understand, temporarily how things fit together. Wilmore and Williams remained on board the ISS as part of Expedition 7172 and returned to Earth on March the 18th, 2025, aboard SpaceX's Crew 9 Dragon. Fantastic. So we've got another organisation there. Of course, they're not necessarily relevant to the safety of the design of this spacecraft, but they're part of the response, part of the control structure. So one of the main things about any hazard analysis is you try to identify hazards, you then analyse them, understand how they can occur and what the consequences are. You'll put mitigations in place, hopefully to eliminate the hazard if you can. And of course, if you can't eliminate it or the potential for it to occur, you'll put some kind of response and recovery in place. And you'll need to think about that as part of the spacecraft design. But of course, when you come to operate a complex system, you should be really thinking about what we do, when this thing's operated and how we respond and recover to the things. And of course, involving SpaceX and their Crew 9 Dragon as a potential response and recovery mitigation is really important, that they're engaged early so that they can be prepared and plan that into their schedule. I mean, I don't know the circumstances. As I said, I've purposefully not gone and read all the newspaper reports and everything to do with this, because I want to start with essentially a blank knowledge with one investigation report and then see where we can go with it. I don't want to bias my knowledge from other information. Okay, so the crewed flight test mission encountered challenges that tested both the spacecraft and operations team. So again, if we're thinking about the concept of a control structure, the spacecraft is under the control and influence of an operations team, so we want to stick them in the control structure. Anomalies included a loss of let's just highlight this, a loss of 6 degrees of freedom control due to reduced thrust from service module reaction control system jets. So we've got the service module, and then we've got the reaction control system jets. Leaks from the helium lines used to pressurize the propulsion system, and then pneumatically operated valves, and a crew module thruster that did not operate during descent. Okay, so that's interesting. There's quite a few interesting elements to this. Okay, so acquiring vehicle operational knowledge, testing new systems and working through anomalies are expected on test flights of a new spacecraft. However, the propulsion system anomalies on the Starliner during the CFT, which is the crew flight test, were more significant than anticipated. The unknown likelihood associated with the reliability of using the service module reaction control system for departure from ISS posed a risk to human life that could not be bounded with agreed margins during the mission. So I just want to highlight reliability there, just as a point, because one of the sort of key tenets of what STAMP is all about is not confusing safety with reliability. Because you could have a really, really reliable system that's dangerous, and you could have a really, really safe system that's really unreliable. So that safety and reliability is not the same thing. And of course, when we start talking about safety through the lens of reliability, we're seduced into talking about things, or trying to talk about things through the lens of probability and likelihood. And of course, when we're talking about issues with inadequate control that are not due to failures, we can't really put a probability on those kind of things. And of course, the more complex the system is that we're talking about, again, we can't meaningfully put a likelihood on things. So this is a bit of a challenge with probabilistic thinking, and especially if we're using traditional methods like fault tree analysis and failure modes and effects analysis, where they almost force you to start sticking numbers in there and try and convince yourself that those numbers are small enough that it's safe to do something, and that's not really helpful in this day and complex age. Okay, so the anomalies experienced during the crewed flight test, and I keep having to remind myself what that is, because when I see CFT, I immediately think of combat fitness test, and I don't know why that's so drilled into my brain, but yeah, it's a crewed flight test. The anomalies experienced during crewed flight test require attention and rigour in resolution. This report provides an in-depth evaluation of technical details regarding the anomalies prompting this investigation, as they are known at the time of writing this report. So let's just point that out. It is important to understand that while much can be learned from this investigation, the testing and analysis that supports the proximate causes of these anomalies is ongoing. So of course it's ongoing. It's not going to be reported in this report. I think they said this is the final report. This investigation also conducts an evaluation of the team dynamics. So there's a team, and they've got some dynamics that created friction throughout the decision-making process to return Starliner uncrewed. Okay, so that's interesting. So we've got it when we're building this control structure. I'm almost thinking that we probably need 2 or 3 control structures, or one big one with loads of detail, and then we need to drill into 2 or 3 versions of it, or views of it, should I say. So one is about the design and the design decisions. One is about the decision to launch the thing, and then another is about the decision to continue on with the mission in the way that they did, and then in this case decide to return the Starliner uncrewed. And despite the anomalies, the extended crewed flight test mission provided valuable data on Starliner's on-orbit performance and offered an opportunity for the Starliner crew to contribute to ISS operations and research. Fantastic. While the crewed flight test, not combat fitness test, while the crewed flight test mission can be remembered as arduous and ripe with lessons to learn, the decisions made in flight ultimately prioritise the safety of the crew and can be seen in hindsight as a successful use of NASA's overarching governance model. Fantastic. I mean, I maybe suggest using STAMP, STPA or CAST to explore that overarching governance model, just to make sure that it is robust and appropriate. Yes, it was successful this time, but that might have been in spite of many issues that are not discussed in this report. I'm not assuming or presuming, I'm just, I recommend using STAMP to look at that. The crewed flight test mission underscored both the promise and the complexity of integrating commercial systems into human spaceflight. Most importantly, it was highlighted that the importance of rigorous systems engineering. Most importantly, it has highlighted the importance of rigorous systems engineering and validation for all future missions. So yeah, I'm highlighting that because systems engineering and validation as a process is underneath the control of some organisations. So there'll be the designer and then the operator and the V&V team and everybody else. And they will have to integrate and make decisions and share information with each other. And so, of course, if that's not happened previously, or if it has been rigorous systems engineering validation, then how did this get through that previously thought to be rigorous and appropriate? Okay, so unique position in humans. In fact, actually, before I go into section 1.2, let's just see if we've got some people chatting to me and I can't see it. So nobody's chatting. So come on, if you want to say hello, tell me where you're from, what you're interested in, what type of things you'd like me to discuss. If there's any experience you'd like to share, either in your own personal domain or in with regards to STAMP, STPA, CAST, or in terms of spaceflight and maybe even this particular case study, please, let me know. So let's have a look at LinkedIn. So we've got no comments yet. Fantastic. Right, okay, so unique position in human spaceflight history. It is necessary to establish context for the time period of the CFT mission. This mission was conducted in a unique period of human spaceflight history. The current era is marked by a transition within NASA and its many partners and providers from predominantly government-owned and led projects to programs and objectives increasingly driven by contracted services and provider-led operations. While there is clear momentum and strategic intent to leverage commercial capabilities, this shift is still in its early stages and many foundational elements are being refined. Okay, so if we were looking at this through the lens of CAST, and I'll just quickly zoom out and we'll go to one of my CAST slides, this one here. So when we're thinking about the control structure model through the lens of CAST, these are sort of 7 areas to think about. This is not an exhaustive list, but these are 7 sort of areas, topics to think about and how they influence and potentially undermine the control structure model. So if we're talking about dynamics and changes, evolution, this section has just mentioned the change and the transition between government-led and funded projects to a more commercial perspective. And so there could be an element of complacency or issues with perception, planned or unplanned changes, or potential for official or unofficial changes that contributed to this. So that's something we could explore, and maybe we'll see a bit more of that as we're going through the rest of the investigation report. So I'll just quickly jump back to where we were, which was over here. There we go. Right, so get it on the screen so you can still see it. There we go. A unique aspect of the crewed flight test, there we go, I'm getting it almost, mission, is the crew's access to options, which is quite unique in the history of human spaceflight. Chief among these was the availability of a stable and highly capable safe haven in low Earth orbit, the ISS. Because of course, if they'd have done this and the ISS was not available for whatever reason, things might have been a bit different. The ISS can support multiple crew members for extended duration and provides an environment that allows for problem solving and contingency planning. This capability provided invaluable during the CFT mission. So maybe, just touching on that little bit there, maybe there is an implied safety requirement for space operations, that there is a need for a safe haven In the World War II, in the English Channel, being from England, World War II, we had the Spitfires flying around trying to stop the Luftwaffe and the Hurricanes and everybody else. And when those aircraft were shot down, they had safe havens in the English Channel where pilots could go into essentially a buoy that's kitted out to give them some survival capabilities, to give them enough time so they can be rescued by fast launchers to pick them up in the channel. Now, of course, this is a similar sort of principle. When you're out in a hostile environment, it is good to have a safe haven. So the fact that the ISS exists is not just for doing science, but also it potentially provides an important function for safe haven in operations. And I mean, I don't know the details because I'm not involved in that organisation. Maybe you do. Maybe you could share and say yes, and the way it's operated, the logistics of it. How many Snickers bars they have on board and how much toilet paper they've got. Maybe they do stock it up for this kind of thing. And if they don't already, then maybe there's an implied recommendation there for people to think about. Maybe there's an opportunity there to create another safe haven, maybe around the moon, for example. That's a hot topic at the moment. So yeah, let's just highly capable safe haven. Let's just point that function out. There we go, safe haven. This capability proved invaluable during the CFT mission. Additionally, the ISS is regularly serviced by a fleet of vehicles, including 2 spacecraft specifically designed for human transportation. The combination of a reliable safe haven and multiple crew transport options created operational flexibility that had not been exercised to this extent. So that's an interesting point. It's not been exercised to this extent. So I'm presuming there's some planning in place already, maybe some exercises, maybe some drills, and they got the opportunity to exercise those. I'm not expecting to see that discussed in this report, but perhaps there's an opportunity to explore that through the lens of STAMP, through the lens of STPA or CAST, and see whether that plan is really as robust as we might think it is, see if there's anything else we could do. Okay, so in some ways, the crewed flight test was the first crewed test flight in the fully commercial model. Although the SpaceX Dragon vehicle completed a crewed flight test in 2020, that flight was preceded by nearly a decade of cargo Dragon operations. Wow, I didn't realise it was that long. I'm getting old, I think. That's gone fast. Wow, a decade of cargo Dragon operations contracted by NASA as part of the commercial resupply service to ISS. During this preceding contracted service, the initial design of Dragon was tested and flown. Many similar lessons were learned and the Dragon design evolved and improved. In contrast, CFT was just the third. That's interesting. It's the third flight of Starliner. I didn't know that. Okay. Interesting. I'm scribbling on the screen behind my head. You can't see it. There we go. Right. A new design spacecraft. The success of a design is not specifically driven by the number of flight tests. Integrated test and supplemental analysis rooted in tests are also keys to success, whether in flight or on the ground. Right, just before we continue then, so just to sort of contrast the two. So the approach that they took with the Dragon, I don't know, I'm assuming that they did it consciously, that they're going to do all the cargo tests, cargo flight, commercial resupply, and perhaps use that as an opportunity to develop and qualify the Dragon spacecraft so that they can make it human crew qualified. But of course, this was the third test of the third flight of the Starliner, a new design spacecraft. So it's not necessarily had the same operational experience as the the Dragon spacecraft had. But what is the decision behind putting a crew on it on the third flight? What's the decision making behind that? What's the safety assessment? What has the hazard analysis shown for that? What did the risk assessment show? And that might be something worth exploring behind that decision making. And then when it says there, the success of the design is not specifically driven by the number of flight tests. Yeah, okay, great. So what is driving that then? What are the elements that might need to be thought about from a program perspective? Program level decision making. Was it justified from a safety perspective? And then now we're sort of thinking, well, actually, maybe we should do small flight tests before we put people on it, or maybe we could do some more representative testing. I mean, I imagine they've done representative testing, but obviously I don't know the scale of that yet. Maybe it's discussed in this report. So while the crew commercial, it's not the Chinese Communist Party, it's the Commercial Crew Program. There we go. It's CCP, right? Commercial Crew Program. So this is the problem with working on so many different platforms and projects and systems. You get so many different acronyms in your brain that when you're trying to read something new, it takes a bit of time just to push the previous acronym out of your brain and replace it with the new one. So let's just read that again. Commercial Crew Program. Right, while the Crew Commercial Program contracted with 2 companies, that's interesting, 2 companies, for the development of 2 transportation services, the companies, their approach to fulfilling the need and the vehicles themselves are different. Well, that's fantastic. That should reduce the reduce risks of not being able to perform whatever the mission is. If you've got 2 people, 2 organisations coming up with 2 different solutions, that should, in theory, manage the risk a little bit. But of course, if you've got 2 very complex systems and they're using more traditional safety assessment methods and not using STPA, then they're going to have similar problems perhaps. Anyway, attempting direct comparisons, especially in a given timeline where the development cycles are in different phases, results in unbalanced conclusions. Yeah, I completely get that. Additionally, SpaceX is a vertically integrated company. That's interesting. Manufacturing many components and systems in-house. Pardon me. Now, just from a control structure perspective, if you have an organisation that's vertically integrated, really, really good, then logically they have tighter control of the design of the safety assessments and the fulfilment of requirements and the behaviours of controllers in that structure than if you have a less integrated organisation, a less integrated supply chain. Because of course you've then got commercial organisations with contracts, trying to contract for things and win business and make a profit and all of those great things. But of course that part of the organisation could potentially undermine or cause problems for doing the actual engineering, doing the safety work. And I've had a lot of experience with that myself over the years. And it is very challenging. But if you do have a vertically integrated company, a lot of those issues disappear and people can focus on the engineering. Now, of course, I don't know the context of Boeing and how the spacecraft was done yet. But of course, having a vertically integrated company probably is a bit more robust from a control structure perspective. But again, I'm only sort of commenting on this from what I know, little I know so far. Boeing uses a multitude of capable subcontractors to acquire hardware. And again, this is not about commenting on capability of subcontractors or anything like that, or their competence. It's just the realities of having a complex, challenging control structure with lots of competing demands from different stakeholders. The less complex it is, the more robust it is. That's all I'm trying to say. To acquire hardware, much of it with inherited design and successful track records. So I'm just going to emphasize a couple of things there. So heritage design and acquire hardware. So maybe it's just the language that this is written. And what I was going to say is this mentions hardware. It's emphasizing hardware. Maybe the issues later in the report are all hardware issues. Maybe it is. If I was a betting man, I'd say there's probably a bit of software in there. There's certainly some organisational dynamics and aspects in there, and probably individual teams. So if we're talking about acquiring hardware, we have to think about the context that hardware comes from a particular control structure. It says here that it's got heritage design, so there's some pedigree to it. It might be really, really good pedigree, or it might have had so many changes over time that it's almost so removed from the previous heritage design that was previously successful that you've got a bit of a Frankenstein. I don't know if that's the case in this case, but we have to be mindful about when we say, well, it's a heritage design, it's got lots of pedigree, just changing the context. You don't even have to change the components or the system itself, just changing the context can introduce new hazards or new causes of hazards. And it says there successful track records. Again, is it a genuine successful track record for exactly the same components in exactly the same context? Or is this slightly different, and does that difference invalidate that assertion? Because quite often, and I've had this happen to me myself, where project management, they assert a particular belief or will. We believe that it's like this, and the more that they say that into existence, that's what the belief and the reality becomes. But actually, when you look at the engineering, just because they've been saying it's one way for many, many years doesn't necessarily mean that the engineering also matches that belief or that assertion. So we almost have to make sure that everybody that's saying things and asserting things are actually backed up by what the engineering is all about and what the facts of the matter of the situation are. Now, of course, I'm talking about past experience. I'm not talking about this. But we just have to be mindful of that. Just because we say something's true, and many people have been saying it for many years, doesn't necessarily mean that that's a fact. Just to call on my experience from previously, there was a Royal Air Force Nimrod aircraft, the Nimrod MR2, tail number XV230, that was lost in Afghanistan in 2006. Unfortunately, 14 people lost their lives. In the aftermath of that, there was various inquiries and investigations and issues, with that. And generally, the view was the aircraft is fine because it's been operating for the best part of 30 years. We've not had any real big accidents with it. Nobody's really died. It's not a big issue. This is the first bad one we've had. Does that actually call into question the pedigree of the aircraft and its design and the way it's been operated and its safety case? Maybe it doesn't. But with any near miss or accident, that implies that the control structure in some shape or form is inadequate. And it's the role of the investigation, the purpose of the investigation, to go and look at that control structure and understand how it contributed to the accident. And that aircraft was very much a heritage design. It was based on the world's first airliner, the Comet, from the 1950s. That was evolved into the Nimrod MR1, the Mark I version of the aircraft. And then that was upgraded to the MR2, the Mark II variant. And as part of those modifications, they included new avionics, which had higher requirements for cooling to keep all the avionics cool. And then, of course, they introduced other functions such as air-to-air refueling, basically in 2 weeks, I think it was, just at the start of the Falklands War in 1982. So previously they didn't have air-to-air refueling capability, and that was a rush modification to get that done. Now, that accident, there's a lot of things going on there. It's very complex. I won't talk about it too much tonight. In fact, I'll probably do a case study on that. If you're interested, comment below and let me know that would be interesting to you. But that was a heritage design too, and it evolved many times over the years. And there were some issues with that heritage design, and more specifically with the safety case, the safety assessment that was done. And I won't go into the detail of that because we'll be here all night. But just be mindful of these claims, these assertions. I know in this case, they might be matter of fact, but just be mindful that, yes, that might be the assertion, that might be the belief. But when you look under the covers, look at the design, look at the operations, look at the safety case, maybe that's not the case. Anyway, I've talked about that. I'll get off my hobby horse now. Neither approach is specifically right or wrong, but worth noting that they are different and thus not a one-for-one comparison. Absolutely fantastic. Thank you. Okay, so establishing actually, before I go on 1.3, let's just see if there's any other questions, comments. If there's anybody giving me any abuse in the comments. This is a live stream. It looks like it's working. I hope it is. Go on, send me a message in the chat. Let me know that you can hear me and that it's working. I'm getting really paranoid now. Anyway, right, so 1.3, establishing the investigation. So in February 2025, the Starliner CFT Program Investigation Team, so these are the stars that did all this work and wrote this report. Fantastic work. Program Investigation Team was chartered by NASA's Associate Administrator, Space Operations Mission Directorate, with details contained in distributed memo. Transition to Program Investigation Team for Starliner propulsion anomalies in International Space Station proximity. This direction established a team to investigate the propulsion system anomalies. Okay, so just to emphasize then, so this report is about propulsion system anomalies. It is not going to look at all of the other things that we could look at if we were using STAMP, using CAST or using STPA. So let's just really underline that so that I don't forget, because otherwise I might talk about all these other weird and wonderful things that are not in the investigation report, and it's just a bit of an exercise. The investigation team has evaluated all events from the initial launch attempt through the currently available post-flight data review. Okay, fantastic. The team's primary objective is to identify the causes and factors behind the anomalies experienced during the Starliner crewed flight test. Let's just check I remember that correctly. CFT crewed flight test. There we go. It's getting in there now. Fantastic. A bit of neuroplasticity, easy for me to say. The team was also instructed to leverage existing data from other investigation initiatives. Okay, such as the Starliner tests and anomalies review investigation. So that's the parallel investigation that's reported in the appendix, I think. And then the Starliner data review team to avoid duplication of effort. Fantastic. The PIT was tasked with evaluating 4 specific aspects of the CFT mission. The root cause, there we go, everybody, root cause, everybody's favourite. So if I was being really facetious, I would say that the root cause of any accident, the primary root cause, is that the control structure is inadequate to enforce safety constraints. There we go. Investigation finished. We've got the answer. I'm being very facetious here, but if we're using a root cause analysis method, it sort of almost psychologically, subconsciously focuses on particular things, and perhaps means that we're blind or don't see or appreciate the broader themes that contribute to the accident. And that's why it's important when we're doing a stamp-based analysis, we always start with, well, what is the control structure involved in this particular situation from an operational perspective, from a design perspective, and if it's relevant to the scope of our investigation, the response and recovery. So just bear with me a second. I think something's not right with my live stream. I don't know why it's doing that. It seems to be, yeah. Just bear with me a second while I try and figure this out. It says it's live streaming, but is it? That is the question. It doesn't seem to be streaming. Does that mean I'm talking to myself, or what does it mean? Something's happening. Why is that not working? Oh. Yeah, I don't know. Can I rewind that and see? Yeah, okay. It seems to be working. I'm unmuted. It says it's streaming. I can see some special numbers telling me that something's happening, and it appears to be on YouTube. So yeah, okay. I'm going to keep going. I trust it's working. Please send me a message. Oh, hang on. Somebody's Wally Wonka. Hello there. Let's get that on screen. Does that work? There we go. Somebody says we can hear you and see you, Simon. Fantastic. I wish the chat would tell me what time that was sent. Because, you see, this is it. So from a feedback perspective, if we were thinking about control loops, me as the YouTuber, so to speak, the live streamer, I'm broadcasting a message to you, and it's going through all of the internet and all the weird and wonderful electronics and software, and it's popping out at your end and your screen. You know, you're sat at home looking at your phone or your computer. And so my control actions, my broadcast is being received on your end. And then there's no feedback for me. I don't know what's going on. I don't know whether it's working. It looks like it's working because I can do I can watch the stream on my YouTube channel locally, but I don't necessarily know whether it's actually getting to you or not. And the fact Wally said something, thank you, Wally, fantastic. Yeah, it seems to be working. Right, I'll take a quick drink and then we'll crack on again. Sorry about that, everybody. These things happen. Imagine if I worked for the BBC. No, don't imagine that. Anyway, right, so we need the screen back on. There we go. So I was moaning about root causes and the focus on root causes. There we go, that's better, isn't it? Yeah, so there will be more causes than just a root cause, and looking for root causes, I think, subconsciously biases any investigation. So of course I recommend using STPA. So we've got helium manifold leaks in the service module propulsion system. So of course, if we just did a control structure specifically looking at that topic, there could be design issues, there could be manufacturing issues, there could be unanticipated issues in service that we'd not anticipated as part of the design. And of course, if we're doing a flight test, did we instrument these things and record that data? Was that a decision we made, or did we not think to do that? Or did we decide, actually, no, we're not going to do that for a good reason, or what appears to be a good reason, but within hindsight could be questioned? If we're talking about the root cause of the service module thruster fail-offs leading to a loss of 6 degrees of freedom control, I mean, they could be completely separate topics. There may be no relationship between those two at all, or there could be a relationship. So when we're building our control structure, we have to think about those aspects. We've got a message from somebody else, Matsumi Saga Walsh. Hello there, good to see you. Really enjoying this session, Simon. Thank you. Fantastic. I'm glad you are, because it's quite hot in this room. And yeah, fantastic. As I say, if you've got any questions, please stick them in the comments, stick them in the chat. Thank you. Right, so crew module thruster failure during entry, descent and landing phase of flight. Okay, so that's a separate topic, but it could be related. That's interesting. Review the culture and team dynamics associated with the near real-time decision-making team and process. Okay, so again, that's perhaps a different control structure model. It will be a different control structure model, but whether we fit it together with the others or not might be different. The objectives of the pit are as follows. So let's keep going. Make sure it's big enough on the screen for you. There we go. So we need to identify the causes and factors that led to the propulsion system in-flight anomalies. There we go. Including issues from previous flights. Okay, so if we're talking about feedback, issues from previous flights is certainly some feedback that you would, that controller will require. Programmatic culture, programmatic resources. So is that money, time, people? If you've got, you could have the best control structure in the world, but if you don't have enough of the right people, you can't recruit people for whatever reasons. There's a whole conversation we could have there about how to recruit safety engineers and retain them and all the challenges with stress and everything else. But if there are holes in the control structure because people can't be recruited or retained, then of course, that's a serious issue. Pre-flight processes, analyses and test plans that led to a go for launch. So this one here, go for launch with reduced system capability, that is a potentially unsafe control action, but it's unfair to refer to that with hindsight. So if we're doing an investigation, we'd refer to this as a contributory control action. There we go, there's my writing with a mouse. Contributory control action. Now when I say contributory, I'm not applying any judgment to that. I'm not saying, oh, all these people are bad and incompetent and it's really bad and all this kind of stuff. I'm not saying that. I'm just saying that decision to say go for launch with reduced system capability, the controller that provided that control action, given that the control action eventually led to the aircraft being in a dangerous situation, you could say that that is a candidate contributory control action. And so if we were, doing the investigation together, we could have a part of our team go off and explore specifically that single contributory control action and say, well, okay, this control action came from this entity, this controller. What was their decision making? What was their control algorithm? What were their beliefs? Why did they believe that it was appropriate to provide a go for launch with reduced system capability? What was their mental model? What was their process model? And of course, logically, what follows from that, in fact, I'll zoom out and I'll use a control structure model. I'm talking away. There we go. Let's just use this loop here. So if this is the decision maker that provides the go for launch with reduced capability, what was their decision making? Were they following a process? Was that decision making a robust process that had all the necessary information available and timely availability? What were their beliefs? What was the feedback that was provided to them? What was the information made available to them to help with that decision? Was it a risk-based decision? Was there some probabilities and failure rates involved in that will sway their decision? So what was the context around the decision maker, that controller? Why would it make sense for them to make that decision? And of course, we know with hindsight that it is related to the outcome. But at the time the decision was made, they probably made the best decision they could with the available information. So as part of our investigation using STAMP, what other recommendations might we make? What other feedback must this controller have to be able to make a good decision? Was the decision making process they followed, was that robust enough to take on perhaps contrary information? Maybe, and I don't know, but maybe there were people that were saying, hey, we know we've got some issues, we don't recommend you launch, and they go ahead and make the decision anyway. Similar to the Challenger launch decision back in '86. Just to put a point on that. Right, let's go back down here then. So we've got, here we go. So this aspect here, that would certainly be a candidate for exploring in detail. Why did this controller make that decision? Why did it make sense? And maybe do a specific study, focus on that ourselves. Develop recommendations for change to future missions, including, let's just emphasize this, recommendations for future change to future missions, including certification, processes, procedures, testing, analytical methods, and in-flight operations. Develop a fault tree for the following system anomalies. That's it. Hang on a minute. The objectives of the pit are as follows. So the pit is going to build some fault trees. Interesting. I would recommend doing an STPA. There you go. Get the pit. Well, in fact, actually, get the people to do a fault tree. If you need help building an STPA, I will jump on a plane and I will come and help you do it. And I'm very, very confident I could find things. And maybe from this case study in the next live streams, you'll see the evidence of those issues we identify that could go further than the fault trees. If I was a betting man, I'd put a bet on it. And if you want to call that bet, send me a message on my website. Right, so here we go. Develop a fault tree. Develop a fault tree. Yes, do that. And then do an STPA and compare the two. For the following propulsion system anomalies: helium manifold leak, service module reaction control system thruster fails off, crew module RCS fail off. Each fault tree is to include proximate cause, immediate cause, contributing factors, organisational factors, observations, and recommendations. What about software? And what about non-failures? Were there any non-failures involved? Will you even find that with the fault tree? No, you won't. Especially if there's loops, non-linear interactions amongst the different layers in the control structure. You're going to really struggle to use a fault tree for that. Fault trees are not designed to find those kind of causal scenarios. Like for example, a decision maker provides a contributory control action because they believed a state of the control process was true when it was not. And that was based on inadequate feedback. That's not going to be covered by a fault tree in any shape or form. So yeah, have a go at doing STPA. That should be a recommendation. If you need a hand with it, send me a message and I will come and help you with it. Assess meeting team organisation structure. There we go. So that sounds a bit like a control structure, doesn't it? Contractor and contractual relationships. So that is the interactions between controllers and the context within which they provide those interactions. Because of course you could have a contract that says do certain things and they are contrary to safety. Because often the safety engineers don't get involved in defining the contract because it's a commercial document. But there may be things in that contract that are actually undermining safety. I've seen that a few times in my experience over the years. Contracting for safety is very, very challenging, very important, and that really can undermine safety a lot. Such as basic stuff like sharing of information. If you're sharing information that informs decision makers and helps them to make safety-related decisions, if somewhere in that chain a commercial agreement or a contract prevents sharing of certain information, that could potentially undermine the safety of an operation or a platform. So, this is all relevant stuff. I could bang on about STAMP all night, which I'm going to. So the effectiveness in team decision making and any potential cultural barriers or organisational factors that contribute to the findings. So that one bullet point, I'd recommend using CAST for that. Produce a findings report that includes all fault trees, evaluating propulsion system anomalies with identified proximate, intermediate and contributing causes, organisational factors and observations and recommendations. So I'm presuming then that this report this report is essentially this document. That's what this is. So maybe there's no opportunity now to do an STPA, but I would recommend it. The full chartering memo titled Transitions Program Investigation Team for Starliner Propulsion Anomalies in the International Space Station Proximity can be found as Appendix F of this report. So let's just jump to Appendix F. So what I'm going to do is I'm going to stick a little reference here, and I'm going to have Appendix F is down here somewhere. There we go. Appendix A, B, C, D. There we go. Appendix F. Investigation Team Chartering Memo. So that was Valentine's Day 2025. Fantastic. So I need an arrow to go to here, to this document. It needs to be a purple one because I like purple to reference things, and I need to zoom out and then drag it right up here. Yeah, if you're interested, this tool I'm using is called Miro or Miro. I don't know if I'm pronouncing it correctly. But Miro. And essentially it's an infinite whiteboard and you can draw on it, add PDFs to it, PowerPoints, all that good stuff, and many other things that I'm not using it for. And I do find it useful, especially for working with clients that are remote. So we can all just log into this, we can talk on Zoom, and we can fiddle around in Miro and do work together, facilitate workshops and training and stuff like that. It is pretty good for that. It's not perfect, but it is pretty good. Here we go, team membership. So the investigation team includes representatives from a variety of disciplines. Fantastic, we like that. It is important to note that multiple members of this team were part of the CFT mission. Okay. That shouldn't be a problem, but, I'm not going to assume or presume. Whilst this could introduce a bias into the findings, the team worked diligently to acknowledge their own experience and solely use evidence-based reporting and or the opinions of interviewees as source data when determining the overall findings and observations included in this report. Okay. The team divided into two sub-teams known as the root cause team and the decision-making teams. The root cause team focused on the technical issues, employing a traditional fault tree analysis investigation. Please have a go with STAMP, please. Of the helium and SMRCS loss of 6 degree of freedom control issues seen during the crewed flight test, the decision-making team focused on the near real-time decision-making process and assessed the cultural issues witnessed during the mission execution timeframe. Okay, that makes sense. Right then. So there's the names, position and the names. I think it will be helpful, and this is just a suggestion for other investigations. If you're going to include information about the investigation team, I do suggest that you include detail about their background or experience in relation to the investigation itself. You don't necessarily have to share names or positions, but it's generally a positive thing to do that. If you can, I understand the security implications. So we've got the PIT team membership, and then we've got technical experts who provided direct feedback or participated in fault tree reviews. Yeah, I can't sort of help feel a bit nervous that it's just about fault trees, or there's a big emphasis on fault trees. I don't think it's enough, especially for something as significant as this, because it is such a significant incident and has very significant consequences. Okay, so let's just have a quick break. Let's see if anybody else has given me some abuse in the comments. If you've not already, please get on LinkedIn, sign in, send me some abuse. And if you're on LinkedIn, I mean, there's loads of people registered to watch this on LinkedIn. I do think now maybe I should have just done it on LinkedIn. So hello, the 75 people that indicated attendance. If you're watching or watching a replay later on, thank you very much for indicating your interest. I think given there's so many of you, I think I'm going to probably do this on LinkedIn next time. But I just wanted to see what YouTube is all about for live streaming, because I think it's got a better response time. I think the gap between me saying something and you being able to see it and respond is about 30 seconds. Whereas with LinkedIn, it's about a minute, and that can make things a bit challenging. So nobody's giving me abuse on LinkedIn. Nobody's giving me abuse on YouTube. So everyone must be having a great time. Right, let's just have a quick drink, shall we? Just bear with me a second. Right, there we go. I'm unmuted, because I wouldn't like to be muted for the rest of the session. Not that I've done that before. Right, so additional investigations. So this section is just 2 quick pages. Additional investigations. Let's have a look. Make it big enough so you can see it on your smartphone screen. Or if you're watching this on your PlayStation, I had a friend I used to work with at the Royal International Air Tattoo. He passed away a couple of years ago now, but he used to be my faithful watcher on his PlayStation. I used to see it in the YouTube statistics. This person watched on their PlayStation. Fantastic. Rest in peace, mate. Anyway, yeah, here we go. So during the CFT mission, a substantial amount of analysis, technical discussion and testing occurred. This work has been built upon in the time since landing. Additionally, several teams were created to investigate portions of the concerns that led to the CFT mission result and propulsion system anomalies. So post-investigation landing efforts, Starliner tests and anomalies review Star investigation team, Starliner data review team, so they were mentioned earlier on. Root cause corrective action team, so RCCA. Again, I don't think RCCA is good enough for this. You need to go further. Enterprise root cause corrective action, ERCCA. In fact, actually, this is Boeing led. I am aware of Boeing having some fantastic STPA facilitators. I'm not going to name names. He knows who I'm talking about. There are a few others. But Boeing, as a company, do have STPA-equipped people in their organisation. And if they haven't got them in this part of the organisation, I highly recommend getting onto the email system and find out where these facilitators are. You should be able to find them quite easily, I'm sure. They're well known, especially in the MIT stamp community. Get them involved in this. And if they're not available, you need help, I will come and help Boeing. Just let me know. I live quite close to a Boeing facility, so that will help. Anyway, here we go. A small workforce of capable engineers was needed to support both the Boeing-NASA root cause corrective action process and the program investigation team process. The PIT received information through the NASA oversight and insight process to create, so there's an oversight process and an insight process to create independent fault tree. Independent fault trees, everybody. Do an independent STPA, come on. Independent fault trees and verified data for the fault tree box closures, because the RCCA activities for helium and SM were in progress at the time of the creation of the pit. For helium and service module RCS, the RCCA team continues through the testing path and campaign while the pit focused on definition of root cause, and forward recommendations. Fantastic. The CM, the crew module, there we go, I'm remembering. Crew module RCS, RCCA investigation was earlier in its investigative state when the pit was formed. The pit took an observational role to the, let's just mark that, observational role. So they are, in terms of control structure, you've got the RCCA team, and then the pit will be receiving some kind of feedback from them to the RCCA team through the development of fault tree for this anomaly. This RCCA effort remains unfinished at the time of the writing of this report. All RCCA efforts must be completed prior to the next flight of Starliner. Do an STPA, please. I'll just give you a little bit of insight in some of the work I've been doing. So I've been working in partnership with a professor from the University of Rome Sapienza in support of the European Space Agency Planetary Protection Panel independent review for the for the Mars sample return mission. And we were invited to do a small STPA project, myself and Ricardo. We found some interesting things that they're really excited about, and we're going to be going over there in May to present our final report. We found some interesting things. I'm not going to sort of divulge and discuss what they are, but honestly, please do an STPA. I keep banging on about it. That's what I'm here to do, but please, you'll find some really interesting things, and they won't be due to failures. Won't be due to just failures. Anyway, right, S-Star report summary findings. Is that big enough on the screen? There we go. So, the Starliner Tests and Anomalies Review Star Investigation Team was established as an internal CCP commercial crew program investigation to identify lessons learned regarding initial certification approaches that could have prevented propulsion system anomalies experienced during CFT. This team looked back at the CCP history, developed design, development, test and evaluation, certification timelines, that's a bit of a mouthful, collected historical data and interviewed personnel with both CCP heritage and current experience. The findings of this investigation, along with any recommendations and lessons learned, can be found in Appendix G. So let's just have a quick look at how big Appendix G is, because I think we should look at that. I think it will be a good idea to look at that in detail. And maybe I should do Appendix G as a specific live stream video. Having said that, yeah, Appendix G, Star Report, SDRT. Look at that, that's really cool. Mission patch. Starliner Tests and Anomalies Review Investigation Team Report. So how big is that then? That's quite large. Let's have a look. 271, 210, so 70 odd page, 60 odd pages. Yeah, we can get through that. I don't know if I'll be able to do 60 pages in one live stream. I might have to split that into two, but yeah, we'll definitely go through that. Okay, the Starliner pit concurs with many findings from the STAR report. The STAR contains significant organisational factors and relevant evidence that are applicable to the observed failures, and serves as a good internal look into CCP in the early days of NASA adoption of commercial services for human transportation. The review and findings of the STAR are specific to the NASA CCP and do not specific to NASA CCP and do not specifically reflect additional contributing factors from Boeing or other NASA entities, ISSP, technical organisations, FOD, etc. So that's important to understand the scope of that work. A thorough review of the STAR report is advised. The PIT endeavoured to supplement the STAR report and not repeat its findings. A sampling of significant findings from the report is included below. Okay, that's interesting. Here we go. Critical designs were set prior to CCT cap. Fantastic. What's that acronym, everybody? Right, well, the acronym will probably be in the acronym list at the beginning, or it'll be at the acronym list. Oh, there it is. Commercial Crew Transportation Capability. Right, let's just make a note of that, everybody. Let's get a sticky note. CC, because I'm going to forget that. I'm going to, unless I repeat it many times. Commercial Crew Transportation Capability. Easy for me to type. There we go. Commercial Crew Transportation Capability. There we go. Fantastic. Right. Let's stick that down here so I don't forget. There we go. Zoom, zoom, zoom. So the critical designs were sent to that organisation for lot lifetime buys of hardware. Ooh, that's interesting. So buying lifetime buys of hardware, I've seen it a couple of times in previous projects many years ago. So the organisation rushes out to buy stuff and they spend loads of money, for very genuine reasons. I'm not being too critical here. So for very genuine reasons, but often that then constrains the actual design and the safety assessments later on. And so they end up with, stuck between a rock and a hard place, which is, well, we've done a safety assessment and what we need is this. We haven't got that. We've got this instead. And actually that is not as low risk as perhaps we'd like. But because we've spent the money now, we're kind of hamstrung into it. The sunk cost fallacy, if you're familiar with that. If you're not familiar with it, do a quick search, sunk cost fallacy, and just watch out for it because it is fatal. Be very careful of it. So that's interesting. So that suggests a bit of a challenge between the supplier and supply chain organisations and their supply chain and buying stuff and the design and safety work that needs to go on. And one of the benefits with using STPA is you can apply that so much earlier in the design process, much earlier than fault tree analysis, and then refine the analysis later on, which means you could probably start making better decisions on what you purchase if STPA was used. And obviously that could save a lot of money, reduce commercial risk, but also improve and reduce safety risk. Okay, so the lot lifetime buys of hardware design resulted in hardware propagation across numerous vehicles and increased impacts for change implementation. Ooh, common modes, anybody? Anyway, resources and skills could have been more adequately addressed during key design activities prior to contract award. Okay. So is this recruitment? I was mentioning earlier on other issues with recruitment, trying to retain people. I don't know. Rigour in resolving issues identified by NASA. So resolving issues identified by NASA during early design reviews could have been increased. That's interesting. That's a feedback loop to think about. So you have a controller that creates something, is passed over to NASA, they review it, NASA provides some feedback during early design reviews, and of course the way those issues were resolved, the rigour of those resolutions under the responsibility of that controller, the rigour could have been increased. Okay, could it have been increased? Is it that they weren't doing the rigour that they perhaps should have done for some, perhaps valid reasons? Or are we suffering with hindsight bias here? Because it's all right saying they could have, but we know that they didn't. So why would it make sense for them not to do that? What was going on? And this is something important to sort of recognise from the principles that underpin STAMP, is we're not here to sort of point fingers and blame people and punish safety into the system. We're here to understand primarily why did it make sense for this particular stakeholder to behave the way that they did. And of course, there's always the possibility that people were just, not doing the job right and cutting corners and everything else, and they're bad or criminals or whatever. But most people come to work to do a good job, so we shouldn't be starting from that accusatory perspective. We should be trying to understand, well, why did the system enable them or hinder them to behave in a certain way? Yes, there may be some bad apples, but it's the system that puts them in that situation. And of course, from a cybersecurity perspective, if you were to use STPA SEC and look at this through the lens of not just good workers trying to do the right thing at work in their context, but also think about the potential for adversaries trying to undermine these things, undermine these programs. From a cybersecurity or physical security perspective, you could also do that. But if you're doing a safety assessment, you generally assume that people are trying to do a good job and have honest interests, honest goals. But also from a security perspective, you could look at this through the lens of STPA SEC and think about, well, what if we do have some potential hostile adversaries that are trying to undermine our programs and perhaps waste billions and things like that? Maybe you could look at it through the lens of STPA SEC. Okay, so shared accountability was applied inconsistently, and NASA incorrectly assumed commercial provider would effectively levy requirements and testing onto suppliers. Okay, so there's quite a lot in that one statement from a control structure perspective. So you've got accountability amongst the different stakeholders in the control structure. Now the question is, well, is that accountability explicit? Is it appropriate given their position in the control structure and the resources available to them? And then, of course, if NASA is incorrectly assuming the commercial provider would do something, well, why did they incorrectly assume that? Was it a reasonable thing for them to assume? Or was it not, formalised in a contract, for example? Or did they not check? Were they required to check? Did they check and the check was not adequate? And then, of course, effectively levying requirements and testing onto suppliers, that is, in this case, the commercial provider providing control actions and receiving feedback from their suppliers below them. So if they've not effectively levied requirements, are there some contributory control actions we need to think about? Yes, there are. And then, of course, if, the suppliers are doing some form of testing, what feedback is the commercial provider getting? And are they actually assessing that feedback as appropriate in line with those requirements? They might be, but it might be inconsistent across the organisation. And I've had example in exactly those kind of situations where suppliers are told to do something, early in the program to get them kicked off, and what do they call it? The lifetime buys of hardware design. Often these contracts are let for subsystem suppliers many years in advance of the delivery, and they're not necessarily coordinated or controlled in a way to make sure that those things and the intent and spirit is actually met. And so when it comes close to delivery date, everyone's in a massive panic trying to do what they need to do, and safety engineers get lent on to perhaps let things through that perhaps shouldn't be. They need more time to close the loops and dot the I's, cross the T's and dot the I's. I've never done that. I've got a very sort of strong integrity in that respect, but it puts a lot of people under a lot of stress and pressure. And if you've got high staff turnover or difficulty trying to recruit and retain people, that could be one of the symptoms of these kind of issues. Okay, so CCP requirements were adequate, but there was no spacecraft propulsion standard to provide guidance on qualification testing. How do you know the CCP requirements were adequate if you're using a fault tree or doing a review? I'm not sure about that, but there was no spacecraft propulsion standard to provide guidance on qualification testing. Well, then the requirements are not adequate, then, are they, if there's no guidance or details on qualification testing? I don't know. I don't know enough about this specific stuff. Right, CCP developed a good set of requirements, including design and construction standards, but not qualification testing. The CCP 1100 series of requirements were deliberately written at a higher level, leaving room for provider innovation, but there was also room for inadequate, incorrect interpretation by the providers. Okay, so the controller is the CCP. They provide requirements. I'm not going to say it's a good set, because that's an assertion. They've provided a set of requirements, but the provider underneath them receiving that has flexibility for innovation, but then there's also the potential for inadequate or incorrect interpretation by the providers. So how was that interpretation sort of agreed or enforced? What's the control loop involved in that? There was no specific design and construction standards levied on this complex system. Which encompasses propulsion qualification and testing at system or subsystem levels. So that's a control. I can't speak. Candidate contributory control action. Specific design and construction standards not provided to the supplier. Okay, commercial. So I'd expect that one. Candidate contributory control action. I'd expect that one to be explored in the control structure model. The commercial provider focused on meeting contractual requirements, language resulting in insufficient demonstration across the component system and ground flight. So for whatever reason, their control algorithm, their decision making is focus on meeting contractual requirement language. But that means that they've not demonstrated sufficiently across the component system and ground flight. So they should have internal auditing or internal quality management that I'd expect would be able to identify and address those kind of things. If they don't, there's a recommendation there. So that's self-assurance, commercial provider assurance. But then also the customer, NASA in this case, how they interacted with the commercial provider to make sure that contractual requirements were met, but also that there was adequate verification, validation and demonstration of important component systems and ground in the context of ground flight. So the RCS thruster testing configuration was not flight-like as it did not... Hang on. The RCS thruster testing configuration was not flight-like as it did not reflect actual duty cycles predicted for the crew flight test. Also, it did not include insulative properties of the doghouse and included active cooling to reduce time between tests. That sounds a bit odd to me. That I think something's missing, and some of those terms I'm not familiar with, so I can't really comment too much. But it sounds like there was a testing configuration which was not appropriate or did not reflect the assumptions. So there's an organisation involved in that and making decisions about configuration and making decisions about flight test and whether it should represent the actual duty cycles predicted for CFT. So why did that entity, that organisation, that controller not do that? Why did it make sense for them not to do that? That should be a specific study. Also, it did not include insulative properties of the doghouse and included active cooling to reduce time between tests. So is that they had a testing configuration on the ground that was not representative of the flight? Oh, that's what it's saying, isn't it? Okay, so it's not... So they've got a representative configuration that's been tested in a way that doesn't reflect the real in-service operational use, the flight test, and that it was set up in a way that it included active cooling to reduce time between tests. So is the inclusion of active cooling, is that a design for the spacecraft, or is it just a design for the testing configuration? And so there's two topics to think about there. The first is, we have to have a representative design and a test. So logically, so why did that not happen? Why did it make sense for that to not happen? And then the second is, well, why didn't the independent organisation that checks this kind of thing not pick this up and question it? Or perhaps they did, but they, their point was perhaps overruled, something like that. So that, again, that's an interest. What is the control structure specifically for the testing regime and the testing configuration? And then, of course, also a bit of a bonus recommendation is if you're a test organisation that has to design tests and test rigs, how do you make sure the testing is safe? How do you assure yourselves you're not going to blow yourselves up? I recommend using STPA, of course. Qualification tests had shortcomings. Great. Okay, what's the control loop around those tests? An independent review of those tests. Suppliers build quality variability issues. Can be hard to exonerate for service modules, which is hardware that is disposed of during re-entry. I mean, I kind of understand what's been said there. Why should we bother doing so? Why should we bother expressing effort and energy and money on something that's just going to get burnt up during re-entry? I get that. But it's got to be safe whilst it's in orbit doing its job or while it's hanging around. So I understand, but that's not really the spirit of what we're trying to do. The AR thermal model included effects of jet firings, but these effects were not validated by ground testing. So the model was not validated. Okay. That's interesting. So the loop for that particular model and the information and decisions that that model supports has not been validated for ground testing. Boeing thermal model did not include the effects of jet firings before. Oh, okay, that's interesting. Thruster performance from OFT1 and OFT2 experienced greater than expected temperatures, and continuing to operate led to a false sense of security of the thruster capability performance. Okay, so I think OFT was orbital flight test, if I remember correctly, and they did 2 of those. This was the 3rd test, and so those tests, those control processes, they will provide feedback into the control structure for use in decision making and design verification and validation for the crewed flight test, and so that control loop that provides that information, that feedback path, should be explored to understand why did this happen in the way that it did. Why was there a false sense of security? What led them to believe that they had security about thruster capability and performance? Flight instrumentation locations for thermal sensors were limited and in different locations than the locations for the RCS thruster ground firings. Okay, so this is 2 configurations. You've got the RCS thruster ground firings configuration, and then you have the flight configuration, and the flight test instrumentation for both were different. So there must be an organisation or some people, a team, that are involved in that configuration control. And why would it make sense for them to configure it in that way? Because there may be some very valid decisions for doing it that way, but it's important to understand why that was. Especially if they've been doing it on previous flight tests. OFT1 and OFT2 investigations did not include reaction control systems and OMAC thruster firings, and fault trees were not validated through subsequent ground testing. So OMAC, I can't remember what that is. Let's just jump back up here and see if we can find it. There we go, OMACK, orbital manoeuvring and attitude control. There we go, everybody. Right. So it did not include firings. So what they're saying then is they didn't do that as part of those flight tests, and they did it for the first time on a crewed flight test. Is that really appropriate? I'm not really sure it is. So who or what is the controller that made those decisions? Why did they believe that that was the right thing to do? Did they even realise that they should probably not do that. And if the fault trees were not validated through subsequent ground testing, okay, why was that? Who or what is the control structure involved in the validation and update of those fault trees? I mean, it could be as simple as, staff turnover, people left. I know that's ridiculous, but the control structure should make sure that those things are done. So why didn't it do that? Both failures and dangerous successes. Limitations of flight measurements and data rates made troubleshooting reaction control system difficult. I think I mentioned this last time. So flight measurements and data rates. So if we go back to our control loop little model over here, if this is us and we're flight testing this spacecraft down here, or we're going to do some testing on the ground, what feedback do we need to be able to make safe decisions, adequate decisions, and provide safe control actions? And that's not just under normal conditions, that's also under abnormal conditions, and perhaps even emergency conditions. Because it may be during normal conditions you only need a relatively slow data rate, but during abnormal or emergency conditions, maybe you need a higher data rate so you can make better, safer decisions. So who decided the design should be the way it is, and why did that make sense? What recommendations should come out of it? Should there be different data rates for flight tests versus normal operations? Or should it be as much data as much as possible, stored and recovered and everything for every flight, no matter what, to aid in the investigation? Because of course, once you lose one of these, in the feared event that one of these things get lost, or there's something really, really bad happening, the investigators need as much detailed information as possible. And especially if you've got a whole, realm of, a whole list of these spacecraft on a production line, if you have an anomaly or an issue with one, you want to get as much data as you can to confirm whether the thing that you're building is adequate or not, or if there's some issues with the design. This is fundamental. And I understand there are limitations with how much data you can collect, record, store, and transmit back to Earth. I totally get that. But always when you're thinking about your designs, your control structures, don't just think about trying to eliminate hazards and respond and recovery from hazards. You should also think about the necessary or helpful feedback that investigators might need to be able to understand this stuff. And especially if it's got complex software in it. Because you might have issues with software, software interactions that, well, it's not really instrumented, is it? So how would you know it's the software causing problems and not just a hardware issue? Anyway, I'll get off my high horse with that one. So let's have a look. So OF4, OFT2, NASA, Boeing did not have tools to measure the thruster degradation, simply treated the thruster as failed operational. Okay, yeah, that's something that should be addressed. Okay, so I'm just looking at the clock. It's now 19:37. I really appreciate you sticking around and watching this. I'm going to do this last little paragraph and then I'm going to call it a night, and I'll reschedule the third one to take part in. And then, of course, once we've got through the report, I'll invite you to actually come on to a live Zoom session with me, a Q&A, where we can actually go through and talk about this actually live instead of just typing away on LinkedIn or YouTube. Okay, so section 2.2, Boeing's Enterprise root cause corrective action. So let's just have a quick drink. Okay, so the RCCA methodology is used to prevent reoccurrence of high severity or complex reoccurring problems by identifying more actual and potential causes. While the technical RCCA teams focused on technical causes for the spacecraft anomaly, the Enterprise RCCA focused on culture, people, processes and tools. This process investigated system, programmatic and technical issues present during system design, verification and flight test that were not fully known, understood or resolved prior to CFT. The results concluded that issues encountered discovered during CFT resulted in increased mission risk. During this investigation process, the systems engineering V was used as a structured tool to integrate the spacecraft's life cycle in order to identify root causes. A summary of the resulting case causes and recommendations can be found in the appendix. Note 1. Labelled in the RCCA report as root cause, as previously noted, the Boeing RCCA team does not utilise the same terminology as the NASA team for fault tree analysis. That's interesting. Yeah, that's interesting. Okay, so I've just got through that. I'm just going to quickly look. What does this hyperlink mean? So just bear with me a second. Where's the investigation report? There it is. Here we go, everybody. Right, page 15, 1516. No, this one. Let's find out what this hyperlink is. It doesn't work. Hyperlink's broken, so we can't check what that process is and whether it's any good or not. All I can really say about that is I've been fiddling around with Stamp STPA and CAST for a long time now, over 10 years now. Well, 2009 was when I was first exposed to it, but I've been doing stuff with it for over 10 years. And I just have to highlight that there are organisations out there that have been using Stamp STPA and CAST for many, many years and getting fantastic results. And they're far, far beyond these RCCA methods. So if you're not already trying to use STPA or CAST, I recommend that you do have a go. Don't take my word for it. Have a look on the MIT PSAS website. Here we go. Look, I'll just zoom in so you can see. There are literally hundreds of papers and presentations on this website that describe other organisations' experience with this, and they present at the MIT Stamp Workshop most years. This year, last week or the week before, we were over at MIT for this workshop. And there are loads of industries. You know, there's loads. There's aerospace, space. You know, there's 76 presentations there that talk about space applications using STPA and CAST. Knock yourselves out. Go and have a look, because, you know, don't take my word for it. Go and have a look at it. And if you need a hand, let me know and we can arrange something. But root cause analysis is just not detailed enough. It's not good enough for complex systems like this. Anyway, I've moaned and complained for the last sort of 90 minutes or so. I hope that is helpful for you. As I say, it is just going through this to read the report, get the information downloaded so we can start building a control structure model and talking about the learning points from using Stamp STPA and CAST. And of course, if you need help with this, please just get in touch. Now, there is another workshop, another Stamp workshop coming up, which this year is been organised by the European Stamp Workshop Committee. And it's going to be held this year at the end of April, 22nd to 24th in Prague. I'm going to be there, so if you want to book a flight, come across, have a conversation, that would be awesome. Prague is a beautiful city, one of my favourite cities if you've not been before. And there'll be an opportunity there to see and talk with other people involved in the Stamp community, learning, applying and getting results with Stamp STPA and CAST. And like I said, if you do need some help and support, just send me a message via my website. Go to Whiteley-Safety.co.uk, click on I need help now, send me a message and we can have a conversation. I just want to say thank you for your attention. This topic is really, really important to me, really close to my heart. I want to bring Stamp to the mainstream, you know, drag it kicking and streaming out of academia, get it into the mainstream and help people like you use this method, gain confidence with it, gain competence and get some fantastic results. So thank you very much for watching, and I will see you on the next live stream. Take care. Bye-bye.